Okay, so now I'll do an example that shows you what I have mentioned before, which is that the work done on a particle depends on the particular trajectory chosen from taking the particle from one initial position to some final position. So in this example, we have a particle which placed at the origin, and we'll take it to the point 3,3 along two different paths. So the first option will be moving completely horizontally and then moving vertically, and the second option will be moving completely vertically and then completely horizontally. And the force that we will apply to this particle is this one. Okay. So let's try to do the first work. So let's go through the first curve. So really this curve has two pieces. Let's call it R1 of t and R2 of t, right? And so the work along the first path is really the work done along the first piece of the path plus the work done along the second piece of the path. Okay, now why do I do that? Because for each of these individual pieces, we know what the position vector is, right? So if you're a particle along this path, notice that the y component is always 0. And then the t component, you can just take x to be t, where t goes from 0 to 3. So you could ask, how did I find this out? Well, this is really the same as, you can write it this way. So this is the same as t10 plus 0, 0. So if you write it this way, notice that this is the equation of a line, right? This is the equation of a line that goes through the origin and moves in the direction of the unit vector 1, 0. Okay, and likewise, you can find an equation for the second path, which is, if you start from this perspective, is a line going through 3, 0 plus t times a vector in this direction, which is j, which is 0, 1. And then you just have to figure out how long it takes you from going to here to here. So at t equals 0, you are at the point 3, 0, so you're here. And how long does it take you to get to this point? Well, it takes you t equals 3, because when t equals 3, you get 0, 3 plus 3, 0, that gives you the desired length. Okay? So this is one way to find the equation of that curve. There are other ways to find this equation, because remember, the way in which you write a curve is not unique, but it doesn't matter which option you choose, but any option will give you the same answer. So the work along the first trajectory equals these two pieces, and remember that the work is just the integral of the force times the velocity, dt, force times velocity, or dot product, dt. Let's do v1 for the first velocity, v2 for the second velocity, and each goes from 0 to 3. Okay, and the force, remember, in this case is x squared y plus 1 comma 0. It only has a component in the I direction, and you're doing the velocity of the first particle. The velocity of the first particle is 1, 0, and that's v integrated against dt, and then plus the integral from 0 to 3 of the force, which is still x squared y plus 1 comma 0, times the velocity of the second particle, which is 0, 1 dt. And you can see immediately that this piece gives you 0, And that just corresponds to the fact that if the force field is perpendicular to the direction of motion, then there's no work applied to it, which is a useful physical fact. So you only have to worry about the first integral that gives you 0 to 3 of x squared y plus 1 dt. And again, you're not supposed to think of these as constants. You have to imagine that you're evaluating these points along the curve. So along this curve, x equals t and y equals 0. So you get the integral from 0 to 3 of t squared times 0 plus 1 dt. And that's just 3, because this goes away. So the first work, let's call it the w along this curve is just 3 joules, or whatever unit you're using. And the point is that we can do the same for the second curve. So for the second curve, let me call this R3 of t and R4 of t. And this gives you W3 and W4. And now we're computing the curve, the work along the second curve, C2. And again, you first need to find the parametrizations of the curve. So again, this is like a line segment. So for R3 of t, the equation of the line is the point, initial point, which is 0, 0, plus t times a vector, which is j in this case, so 0, 1. And again, you need 3 units of time to get to 0, 3 under this equation. And for the second one, the initial point can be 0, 3 plus t times the velocity vector in this direction, or the direction vector, which is I, so is 1, 0. And again, you can take t to go from 0 to 3. So it's a similar story. We get the w, the new w is W3 plus W4, okay? And this is the integral from 0 to 3 of f dot v3, the integral from 0 to 3 of f dot v4, and this gives you 0 to 3 of x squared y plus 1, comma 0. v3, the velocity in this case is 0, 1, plus the integral from 0 to 3 of x squared y plus 1, 0, dot the derivative here is 1, 0, so now it is the first integral that becomes 0, because now you're moving vertically but the force field horizontal. So this is the first now in this case this one gives you 0, and so you just end up with the integral from 0 to 3 of x squared y plus 1 dt. But again, these are not constants. They are evaluated along the curve. Which curve? Well, now you're using this piece of the curve. So notice that along this piece of the curve, you can use this equation. Notice that on R4, if you combine them together, this is of the form t, comma 3. So that means that along R4, along this curve, x equals t and y equals 3. So you get the integral from 0 to 3 of t squared times 3 plus 1 dt. Notice that as opposed to the previous case, now this is no longer 0. So now you can see immediately that there will be a difference between the two works, because this integral will be t cubed plus t let's see, yes, from t equals 3 to t equals 0. And so this gives you 3 squared is 3 times 3 times 3, so it's 27 plus 3, that's 30. So the work along this other trajectory, you need a lot more work to be applied. It has to be 30. So this shows you the trajectory matters. And so the next step that we want to discuss is are there circumstances where we can guarantee that no matter which trajectory we have chosen, the work would be the same. And those cases do happen, and when that happens, we say that the vector field or this force field is conservative. So we'll start talking about conservative fields next time.